The Chiba Urban Monorail is a suspended monorail system in, you guessed it, Chiba, Japan, near Tokyo. It's the longest in the world, with a system length of 24.5 miles. It's a rare configuration for public transport, with fantastic views of the passing city, a sci-fi glimpse of passing buildings from several stories up, and an unobstructed view of the path ahead. It takes about an hour to get from Chiba to Tokyo, which lies on the other side of Tokyo Bay. The Chiba Urban Monorail is a fascinating sight if, like me, you're not used to public transportation hanging above you. These stations are peculiar as well. Most public transportation takes places in an artificial light tunnels deep underground. Not here. The stations are open, breezy, and sunlight.
Is symmetric, meaning the left side is going to be equal than the right side. And for this, we can use the y forces to know AY and JY. So we have to do this. AY plus JY minus these 65 kilonewtons forces are going down. That's why we're going to subtract. So we're going to subtract these 65 kilonewton forces. These are exactly 4, 5, 6, 7, 8, 9 forces. 9 times 65 is going to be 585 kilonewtons. Okay, as we already know, AY and JY are going to be the same. So in order to get these reactions, we have to divide 585 by 2. This is 292.5. In order to solve the truss, we need to find the forces that act on joint A. First, we made the free body diagram, and this is what we get. 292.5, that is the reaction force, and we have also AB and AS, which are unknown for the moment. First, we have to find AS in the summatory of forces of Y. We need to put this 292.5 plus AS times sine of 75.52. With this, we get that AS is 302.09. Now that we have what AS is, now we can put it in our Fx equation, which will be minus 302.09 times cosine of 75.22 plus AB. Now we isolate AB and we get that AB is 75.52.
Second joint will be joint S. As we can see in the free body diagram, we have a force going down of 65 newtons, and we have a force pushing the joint with 302.9 kilonewtons. So first we will solve the sum of forces in Y. That will be equal to 0. Minus 65 plus 302.9 sine of 75.72 minus SB sine of 75.72. Doing the math, we get that SB will be equal to 234.96. Then, with this answer, we can plug it here in the sum of forces in X equation, and we'll get that SR will be equal to minus 134.25. This tells us that SB is in tension and SR is in compression.
34.96 in compression as well, and the 65 kilonewtons that is over here of the train. First, we have to solve Fy, which is Fy equals 0, and this is equal to negative 65 plus 234.96 times sine of 75.52 minus Rc, which is an unknown, times sine of 75.52, which is the angle of Rc. Solving this equation will get us that Rc is equal to 167.83. This one is positive, meaning Rc is in tension. Now that we already have Rc, we have to plug it in the f of x equation, and then we'll have 134.26 plus 234.96 times cosine of 75.52. Then we have to add 167.83, which is Rc, multiplied by 75.52, and then add Rq, which is the variable we're missing. Solving for Rq, we get that it is equal to negative 234.96. This means that Rq is in compression.
So now that we got the other answers, which are forces Bs and force AB, that force Bs is 234.96 and force AB is 75.52, we can calculate for BR and BC. In order to do that, we do the summations for Y, and by doing that we get BR sine 75.52 plus 234.96 sine 75.52 equals to 0. And solving the equation, we get that BR is equal to minus 234.96 sine 75.52 divided by the same angle, so we can avoid it and eliminate it by crossing it out. And then we get BR is equal to minus 234.96 kilonewtons. We just got the answer for force BR. So once we get that, we can calculate for forces in X. Doing that, we get this equation, which is minus 234.96 cosine 75.52 minus 75.52 minus 234.96 cosine 75.52 plus BC. And solving this equation, we get that BC is equal to 192.99, that we can write it as 193.0.
For joint C, we have these forces in this joint. We have a force of tension that is equal to 167.83, and this one that it's also tension force going like 192.49. First, we make the sum of forces in Y, having this, that 167.83 sine of the angle plus CQ sine of the angle. By solving this and rearranging the numbers, we get that CQ will be equal to minus 167.83 sine of 75.72 over sine of 75.72. This will be equal to 1, so we neglected. And we get that CQ will be equal to minus 167.83. Then, because we have we now have this value, we can make the sum of forces in X minus 192.49 minus 2 times 175.83 cosine of the angle. Because these two will be facing the same direction and they are equal in magnitude, we can assume that they are the same and we put a 2 here. Solving for CD, we get that CD will be equal to 276.89.
We're going to solve joint D. And to solve joint D, first we need to make the free body diagram, and we have tension force in here and in here, which are 276.84 and 100.70. We also have dP and dE, which are unknown. First we have to do the summatory of forces in Y, which is equal to 100.70 times sine of the angle, plus dP sine of the angle as well, which is equal to 0. Then we have to isolate dP, which is equal to negative 100.70 times sine of the angle over sine of 75.52. We cross out the sines of the angle and we get that dP is equal to negative 100.70. Now that we have that dP is equal to minus 100.70, this means this force is actually in compression, which will result in negative when we do the f of x equation. This will mean that negative 276.899 minus 2 times 100.7 cosine of 75.52 plus dE will get us the force we're looking after, which is dE. We isolate dE and we get that dE is equal to 327.27. This force is positive, meaning it's in tension.
Solving for joint P. In joint P, for the forces, for the unknown forces, the sum of forces in Y will be equal to 0. So 0 will be equal to minus 65 plus 100.70 sine of the angle minus PE sine of the angle. Solving for PE, we get that PE will be equal to 33.75. Then we get the sum of forces in X will be equal to 0 because this is an equilibrium. Then we get that 302.9 plus 100.70 cosine of the angle plus 33.75 cosine of the angle plus PU plus PO will be equal to 0. Solving for PO, we get that PO will be equal to minus 335.66.
So once we got all the forces before, we can go and pass to the joint Q and analyze to that part. In order to do that, we get the summation in Fy, and we get 167.83 sine 75.52 minus 65 minus the force that we are trying to get. And once we solve that equation, we get QD 100.70, and that's the force to QD. Then we get the summation in the forces on X, and we get 234.94 plus 67.8 cosine 75.52 plus 100.70 sine NSCM5278 plus QP, that is the force we are looking for. And once we do all the operations over there, we get that QP is minus 302.07, and that is for this part in axis X.
So now we're going to do the same truss by another method, which is the section method. For this method, we have to make a cut, and we can only cut three forces at most. These forces are the ones that we're going to calculate. For example, if we cut in here, we're going to calculate the force DE, PE, and PO. So the main difference between this method and the joints method is that in this method we use the three equations, which are moments, forces in X, and forces in Y. So we're going to start in here, and we're going to make this the first cut.
We finally got to this point, to the point to analyze, which is joint E. And for that, we get this equation that we're looking for, the force OE. And solving for OE, we get that OE is minus 33.57. Once we got that, we can write it over here. And as you can see, this is the diagram for joint E, which is the one that we are analyzing right now. And then we pass to the forces in X. And solving this long equation over here that we are looking for is force EF. We get that EF is 344.05 kilonewtons. In doing that, we understand that the force acting on O to E is a force in compression, is a compression force. We can write it down, drawing down with red color, with a red marker, and then we get that EF is in tension, and we can write it down on green marker. Now, this is a very important part because we just finished analyzing half of this structure, and once we did that, we understand by looking at it and analyzing all the forces that act over here, we can say that this part is symmetrical to the other part, and by doing that, we can just and put the colors to the forces that are acting over here, because we already know what's happening in real time here. And as you can see, this is the only part of the structure that is going to have two forces in compression connected to the only joint, which is over there. And then what we can do next is draw all the other forces that are acting, and we will get a symmetrical structure. And we do this, and then all these joints over here are connected by forces in tension, and then we get another forces in tension right here, and right here, and over here, and we get finally we get all the forces that are acting on our structure, and we get this diagram, which is so accurate.
Now we're going to start with the section number one. We make the free body diagram, which we have three forces: Kj and Ij, which are unknown, and 292.5, which is the force in the support. We have to find Kj with the summatory of forces in Y, which is 292.5 plus kj times sine of 75.52. We isolate kj and we have that kj is equal to negative 302.09. Now that we have this force, we can plug it in here and find and find ij with the summatory forces in x. This means we have negative ij plus 302.09 times cosine of 75.52. We isolate ij and we get that it is equal to 75.52.
Section 2. In section 2 we have a force that's going down of 65 and the force is going up of 292.5. First, we do the sum of moment, it's equal to 0. In this part we're gonna apply the moment in this point. So we can isolate these three forces and we only have these two. So we measure the distance between the points and then in our equation. So we have 1.5 this distance multiplying 292.5 minus 5.8, which is our height, times ij, it's equal to 0. Isolating ij, we get that ij is equal to 35.72 kilonewtons. Now having this force, we can start doing the sum of forces in y. That will be equal to 0. 292.5 minus 65 minus ik, sine of the angle. Doing the math, we get that ik will be equal to 234.96 kilonewtons. But finally, we get the sum of forces in x, and the equation will be 234.96 cosine of the angle plus lk plus 75.52. And isolating for the lk, we get that it's 139.96 kilonewtons.
To section 3, and when we get to this point, we're going to have certain forces that we know, which are the one that is 65 and the other one that is 292.5. Now we do this summation for forces in axis y, and we get all these, and by solving this equation we get the force that goes from L to I, and that is minus 234.96. And when we get this, we can write it over here. After we do that, we can go to the other equation, and when we solve it, we get the force that goes from L to K, and that is 100 minus 134.26. And then passing to the other part, we go to the forces that are acting on axis X, and that is when we solve the HI, which is 193.0, and that should be all forces on that diagram over there.
Now we're going to do the moments in the point L. This is going to be equal to HI times its perpendicular distance, which is 5.809, minus 65 times 3 plus 292.5 times 4.5. We isolate for HI and we get this, that it is equal to negative 1121.25 over negative 5.809. Then we solve this and we get that HI is equal to 193. Now that we have all the forces, we can solve for LM with the summatory of forces in X. This will be equal to negative LM minus 167.83 times the cosine of 75.52 minus 193.01. This will be equal to 0, and we isolate LM, and this gets us negative 234.96.
In section 5, we have 3 forces acting in this thing, and 3 unknown forces. We have 65 and 65 going down, and we have 292.5 going up. So first we do the sum of forces in y. That will be 0 will be equal to minus 65 2 times plus 292.5 plus mh, sine of the angle. Solving for mh, we will get that this is equal to negative 67.83. Then we do the moments, the sum of moments. That will be equal to 0. ml by 0.5 by 5.89, 80 plus 9 because minus 65 times 1.5 minus 65 times 4.5, this distance, and we have plus 292.5 times 6, which is this distance. Then we get that we solve for ml, and we get that is equal to negative 234.96, and then we get the sum of forces in x. That will be minus gh plus 167.83 cosine of the angle plus 234.96. Solving for gh, we get that gh is equal to 276.
So this is section 6, and for analyzing the system, we go to this model right here, and we see that we have 3 forces acting over here, which are 65, and then using this equation we can determine forces going from G to H. In solving that equation we get 276.92 kilonewtons, and then in order to solve, we can write it over here, and then for solving the other equation, in order to solve the other equation, we get forces going from G to M, and that's 100.70 kilonewtons. And then we solve equations for forces acting on x-axis. In doing that, we get this equation, and on this equation, we're looking for forces going from joints N to M. In doing that, we get NM equals to minus 302.9 kilonewtons. And this is our diagram, which is very clear, and we can list every force we have over here in order to continue and get the other ones.
We're going to proceed with the section number 7. We make this free body diagram, and we find these 3 forces of 65 kilonewtons. This 292.5 force, that is the reaction, and these 3 unknown forces, Nm, Ng, and Fg. First, we need to find Ng with the summatory of forces in y. This will be equal to minus 65 times 3, because there's 3 of these forces, plus 292.5 plus ng times sine of 75.52. We isolate ng and we find that its value is negative 100.70. Now we proceed with the moments in the G point. And for this we need to put Nm, which is an unknown force, times 5.809, which is the perpendicular distance to this point, minus 65 times 1.5, minus 65 times 4.5, and minus 65 times 7.5. Then we add 292.5 times 9, and we isolate Nm. This will be equal to negative 309, negative 302.09. Now we're only missing Fg. To get Fg, we need to make the summatory of forces in x. This will be equal to 100.70 cosine of 75.52 plus 302.09 minus Fg. We isolate Fg and we get that its value is 327.27 kilonewtons.
Section 8. In section 8, because it's a section, it's a cut that's far away from the origin, we have a lot of more forces acting in this system. But it doesn't matter because we only have 3 forces that we don't know, so we can still apply the 3 equations of equilibrium. First, we start with the sum of forces in y. It will be 65 4 times, because there are 4 times and 65. There are 4 forces of 65 going down, plus 292.5 minus NF sine of 75.72. Solving for NF, we get that NF will be equal to 33.56. Then we get to the part of the sum of moments. We get that 65 times GF times the height, minus 65 times 3, minus 65 times 6, minus 65 times 9, because these are these points. 292.5 times 10. Solving for GF, we get that GF will be equal to 325.29. Then we only get the sum of forces in X. That we want to find NO. We got 33.5 cosine of the angle plus 327.29 plus NO. Then we isolate NO, and we get that NO will be equal to minus 335.66.
So this is the last part to analyze, which is section 9, and we have, as you can see, many other forces, and we're looking for EF, OF, and ON. And by doing that, we can see the procedure right over there, and solving the equations, we get that OF is minus 33.57. And then by doing the moments equation, we get that ON is minus 335.66. And by solving the last equation, which is X equation, we get that EF is 344.05. And we get all these forces, and we already know that, and they are listed here. And as we already said, as we already did, the whole structure is very symmetrical. So for this part, as you saw at the beginning, we started on the other side in order to get the same results and in order to prove that we got the same results for every force. And that's true. If you want to compare our last examples, you will see and you will notice that they are the same forces. Some numbers may vary, but they are very little, very small numbers. And so we as we said, this is the last part. In further, we will explain that the symmetrical structure is not as complex as it seems. And once we solve the half, we can take the other half and solve it again with another method, and that's what we did.
We just finished filming the sections method and the joints method, and now we're going to make our conclusions about the project.
Yeah, as you can see, we have our model here, and this is very important to understand every force and the whole structure. This is made with wood and certain types of other materials, and this is an abstraction of how the forces act on the bridge right here.
As we already mentioned in the video, the forces that we made was only the half of it. As you can see, this model is the same in the left side and the right side, meaning that this force will be equal to this one, and this one will be equal to this one in same magnitude and same symbol. Also, we can find that this model represents in the upper part, all the forces are in compression, and as my companion will say, we will explain why it is that way and why the part in the bottom it's all in there.
As we can see, all our weights are going down. That means that our structure will be making this little thing like this. That's why we have compression in this part and we have tension in this part, because the structure is going down and the first parts are trying to compress and the bottom parts are expanding. That's why we have tension in this part. In this part we have like compression and tension alternating. Only in the center we have compression and compression. That's because we need this compression because the thing's going down. And this is to equilibrate this compression, and the same for this, and the same for this, and the same for this. Just in the middle we have two compressions because the structure, the two symmetrical parts of the structure are like fighting each other. It's a point where they are pushing each other.